Welcome to the Deep Dive. We're the show that plunges right into the source material, cuts through that noise, and pulls out the key knowledge nuggets just for you.
That's the plan.
And today, we are really diving deep. We're looking into the, well, surprisingly complex world of tracking tiny moving particles, especially when they're in really messy, crowded places, like, those live cell videos you see in biology labs?
Exactly. And our source today is a pretty recent academic paper. It introduces a really interesting new method for tackling this specific problem. They call it the Attention-Bayesian hybrid approach. ABHA for short.
ABHA.
Yeah, and it's quite neat because it tries to blend, cutting-edge machine learning, the attention mechanism, with more established sort of classical techniques.
Right. So our mission today, sticking strictly to what's in this paper, is to really unpack ABHA. We want to understand the tricky problems it's trying to solve, really zero in on the, let's say, the academically innovative parts.
Mm-hmm. The core ideas.
Yeah, the core ideas, and see how the authors themselves show it stacks up against, well, the existing ways of doing things.
Sounds good. Let's dig in.
Okay, let's get to it. Now, tracking. It sounds simple, right? Just follow the dots moving around. But the paper makes it really clear that tracking multiple tiny particles all at the same time over time, especially in, like, a crowded cell, or they mention these patches from images.
Yeah, like in their figure 1, you see these little tracks in a crowded box.
Exactly. Why is that so incredibly difficult?
Well, the fundamental problem, and this is really what ABHA is built to address, is something the paper calls the combinatorial explosion of trajectory hypotheses.
Okay, combinatorial explosion. Break that down.
So imagine you've got a dense scene. Lots of particles buzzing around. In every single video frame, you detect a bunch of spots, your measurements. The hard part is figuring out which spot in this frame connects to which spot in the next frame.
Mm-hmm.
And you have to do that for every particle all at once over, maybe hundreds of frames.
Right. So if I've got, 20 particles, 100 frames, that's 20 little paths I need to connect. But at each step, any spot could belong to particle A or particle B, or maybe it's just noise.
Precisely. The number of possible ways you could connect those dots, all the potential paths or hypotheses about who went where, it just grows incredibly fast. The paper uses the term super-exponentially.
Super-exponentially.
Wow. I mean, it doesn't just get big, it gets computationally, well, basically impossible to just list out and check every single possible connection history. It's overwhelming.
And then to make it worse, the paper points out the detections themselves aren't perfect. They can be noisy and spurious.
Exactly. So you might detect something that isn't really a particle of false positive, or you might completely miss a particle that is there a false negative.
So the puzzle pieces themselves are dodgy.
Right. You're trying to solve this gigantic connection puzzle, but some pieces are missing and some shouldn't even be in the box. That uncertainty just feeds the fire, making the association problem, figuring out who's who, even harder. It fuels that hypothesis explosion.
Okay, so that's the mountain to climb. Given this huge combinatorial problem space, how did people usually try to tackle this before something like ABHA came along? What were the limitations mentioned in the paper?
Well, the paper talks about traditional methods, specifically Bayesian filtering approaches.
Yeah.
And it mentions multiple hypothesis tracking, or MHT. MHT gives you a solid probabilistic framework. It's actually designed to handle multiple possibilities. It maintains and updates several different trajectory hypotheses simultaneously, tracking the probability of each scenario being correct.
And the paper does say MHT can be optimal sometimes?
Yes, it can be. It's potentially optimal, very effective, if the number of possible connections, the number of hypotheses you need to track, is reasonably small. Or if the problem's already been simplified somehow, it's got a strong foundation for predicting a particle state and updating that based on measurements.
But if the hypothesis set is small, that sounds like the exact opposite of the noisy, cluttered situation we were just talking about, the one with the explosion.
And that's the crux of the limitation, as the authors see it. MHT works by trying to explicitly manage all those competing possibilities, using what they call a purely Bayesian combinatorial association strategy at every single time step.
Okay.
So when you hit those really noisy, cluttered scenes, and that hypothesis space just blows up, MHT gets bogged down.
Yeah.
It becomes computationally way too expensive, basically impractical, because it's trying to juggle far too many possibilities.
Right, it gets overwhelmed. Okay, so traditional methods struggle with the scale. What about deep learning? Neural networks seem to be solving everything these days. How do they fit in here?
Oh, deep learning has definitely been applied. The paper mentions RNNs, recurrent neural networks. They're generally good with sequences, like particle motion over time. And they've been used effectively to model the dynamics, how a particle tends to move based on its history. But the paper points out a key weakness. Their sequential nature makes it hard for them to handle the really complex association part efficiently. Figuring out simultaneously which of many detections belongs to which of many tracks across different frames.
Okay, so RNNs are good for the how it moves part, less so for the who is who part in a crowd. What about transformers? They're the big thing now.
Transformers get a specific mention, yes, especially their self-attention mechanism. The paper notes they've shown, and I quote, significant improvement in robustness against this high combinatorial load.
So they can handle the load better.
Apparently so. They seem much better at narrowing down possible associations. The idea is that attention lets the network look at all the detected points within a certain time window, kind of all at once, and learn the complex relationships between them. That helps it sift through that massive cloud of potential connections more effectively.
Okay, so transformers sound promising for the combinatorial mess, but the paper also flags a potential downside, right? Compared to MHT.
Yes, exactly. The authors, and they seem to be building on their own prior work comparing these things, they point out that a transformer might actually be suboptimal when the situation is simple, when the hypothesis set is small, which is where MHT did well. And maybe more fundamentally, they argue that a complete reliance on a transformer structure limits interpretability and adaptability. You kind of lose that clear model-based insight into why it's making certain connections, the kind of insight you get from something like a Kalman filter within MHT. It's more of a black box.
All right, this sets things up perfectly. We've got this massive challenge. Tracking and clutter leads to this combinatorial explosion. Traditional methods like MHT are rigorous but choke on the complexity.
Right.
Deep learning, especially transformers, can handle the complexity, that sheer number of possibilities, but maybe they aren't always optimal and you lose some interpretability. This just screams hybrid approach, doesn't it?
It really does. And that's precisely the motivation behind ABHA, the Attention-Bayesian hybrid approach. The paper explicitly calls it a modular hybrid tracking framework.
Modular, meaning separate parts doing specific jobs.
Exactly that. The core innovation here, the key insight in the paper, is realizing you can split the problem into two main chunks. First, there's the incredibly messy association problem, figuring out which detection goes with which track. That's the combinatorial nightmare. Second, there's the state estimation problem. Once you have a set of points you think belong to one particle, figure out its precise position, velocity, and so on.
And ABHA uses different tools for each chunk?
Yes. It tackles that first super hard association part using a learned attention-based method, the transformer. And then for the second part, the state estimation, it uses a classic, reliable method, Bayesian filtering.
So the transformer's power is aimed squarely at taming that combinatorial chaos first.
Right.
And then it hands off a cleaner problem to a traditional tracker.
That's the core hybrid idea. The paper puts it nicely. Combining an attention-based approach for pruning hypotheses and a Bayesian approach for tracking using those prune hypotheses offers a promising solution, especially for these cluttered scenarios. The transformer does the heavy lifting of pruning that enormous tree of possible connections.
Pruning, like trimming branches off a tree.
Exactly. It cuts away the unlikely connections. Once that's done, you're left with a much smaller, much more manageable set of high-probability connections. Then you bring in the standard Bayesian filter specifically. They use Kalman filtering to do the detailed state estimation along these simplified paths.
Got it. Transformer cleans up the mess. Kalman filter does the precise calculations on the tidied up data. And the paper mentions this modularity helps with robustness and interpretability.
That separation is crucial. You get the best of both worlds, hopefully. The transformer's strength is pattern recognition in complex data, perfect for the association task. But then you retain the well-understood, interpretable, and efficient Kalman filter for the actual tracking part, which it can handle easily once the hypothesis set is pruned.
Okay, let's really dig into the mechanics then. How does this ABHA framework actually work? Stage 1, the hypothesis pruning with the transformer. How does it frame data association as a label prediction problem?
Right. So instead of trying to build and score every conceivable trajectory, which we know is infeasible, the transformer is trained to do something different. For every single detection, it predicts a label.
A label.
Yeah. Basically, it predicts which existing track that detection most likely belongs to, or if it's likely the start of a brand new track. It assigns a category, a label, to each point.
Okay, can you walk us through the steps, maybe using your figure 2 as a guide?
Sure. So the input is your raw data, detected positions, and the time they occurred, usually from a batch of frames time window. These inputs get converted into embeddings, numerical representations that capture information about the detection and its time position.
Embeddings, okay. Standard deep learning stuff.
Pretty standard. Then these embeddings are fed into a transformer encoder.
And that's where the attention happens.
That's the key part. The self-attention mechanism inside the encoder allows it to look at all the detections within that window simultaneously. It learns the relationships, which points tend to appear near each other, how they move relative to others over time, the patterns and the chaos. The output from the encoder is a set of refined representations for each detection, now packed with contextual information gleaned from all the others.
Okay, context-rich representations. How does that lead to the pruning?
Each of these refined representations then goes through a couple more layers of feed-forward network, then a final layer that outputs probabilities using softmax. The final output is this crucial thing they call the association matrix, matrix A.
Matrix A.
Got it.
What's in that matrix? What does it tell us?
Matrix A is the heart of the transformer stage's output. Think of it like this. Each row corresponds to one of your input detections. Each column represents a potential trajectory label, track 1, track 2, track 3, or maybe new track.
Okay.
The numbers inside the matrix are probabilities. So the value in row 5, column 3, tells you the probability that detection number 5 actually belongs to trajectory number 3.
Ah, okay. So the transformer essentially says, for this detection here at time t, I'm 85% sure it's part of track 2, 10% sure it's track 5, and, negligible probability for anything else.
Exactly that. It provides these soft associations, these probabilities, linking detections across frames. And this matrix is the learned pruning. The high probabilities point strongly to the most likely connections, allowing you to effectively ignore the low probability ones.
Makes sense. How do they train the transformer to predict this matrix A accurately?
It's supervised learning. They need ground truth data examples where they know precisely which detection belongs to which real trajectory. This gives them the true association matrix. Let's call it A.
Right, the answer key.
The answer key, exactly. The transformer is trained to make its predicted matrix, A, look as similar as possible to the true matrix, A. They use a standard method for this, a cross-entropy loss function, to measure the difference.
Okay, but what if the transformer predicts track 1 goes with true track 2 and vice versa? The columns might be mixed up.
Good point. They handle that using the Hungarian algorithm during training. Before calculating the loss, the Hungarian algorithm finds the best way to match the predicted track labels, columns in A, to the true track labels, columns in A.
Ah, so it lines them up correctly first.
Yes, insurers are comparing the right predictions to the right ground truth tracks. The paper also mentions they use a metric called JSCA Jacquard, similarity coefficient for associations during training, to monitor how well the predicted groupings match the true ones. They aim for a high JSCA, like over 0.8.
Okay, so the Hungarian algorithm helps compare apples to apples for the loss calculation. Once trained, you feed it new data, it outputs matrix A. How do you use that to feed stage 2?
It's actually quite direct. For each detection, each row in matrix A, you just look across the columns and find the trajectory label with the highest probability.
The maximum value in the row.
Exactly. Use an argmax operation. This assigns one single, most likely trajectory label to every detection. What this does is effectively group together all the detections that the transformer thinks belong to the same trajectory segment. It creates that prune tree of trajectory hypotheses we talked about, a much simpler input for the next stage.
Which brings us to stage 2, state estimation. The transformers sorted the detections into likely tracks. Now, what does the Kalman filter do?
All right, now the classical Bayesian part takes over. You've got these sets of associated points, these likely trajectory segments. Standard Kalman filtering is then applied independently to each identified segment.
And Kalman filtering is? Remind us briefly.
It's a very well-established recursive algorithm. It's designed to estimate the state of something that's changing over time, like a particle moving, even when your measurements are noisy.
And the state here is usually position and velocity.
Typically, yes. Position and velocity. The Kalman filter operates in a predict-update cycle. First, based on a motion model like assuming constant velocity, which the paper mentions using specific matrices F and Q, for the model it predicts where the particle should be in the next frame.
Makes a guess.
An educated guess, yeah. Then, when the next measurement arrives at a detected point that the transformer associated with this track, the filter updates its estimate. It combines the prediction with the measurement, considering how uncertain each one is, using other matrices, H and R, related to measurement noise, to get a refined, more accurate estimate of the particle's true state.
So predict, measure, update, predict, measure, update, over and over.
Exactly. And here's a really crucial point the paper makes. The Kalman filtering model used in ABHA is the same one used in the MHT baseline they compare against.
Oh, interesting. So the filter itself isn't the innovation here.
Precisely. The novelty in ABHA isn't a new type of filter. It's the sophisticated learned attention front end that pre-processes the messy data and figures out the associations. It feeds the standard efficient Kalman filter a much cleaner pre-sorted set of points to work on. The transformer solves the hard association problem, which lets the Kalman filter do its state estimation job effectively without getting swamped by that combinatorial complexity.
That really clarifies the division of labor. Transformer handles the combinatorial association mess. The proven Kalman filter handles the state estimation on the cleaned-up tracks.
Okay, so how did they test if this actually works better? How did they evaluate ABHA? They tested it using data from a benchmark challenge, the ISBI particle tracking challenge, specifically the virus's dataset. They didn't use full images, but these small 30 by 30 pixel patches.
Okay.
These patches are designed to mimic realistic, challenging conditions you'd find in biological imaging, crowded scenes, particles doing sort of stop-and-go movements, and different levels of noise and clutter added in various test tasks.
And how did they measure success? What metrics did they use?
The main metric they highlight, and it's a really good one for this problem, is called TGOSPA. That stands for Trajectory Generalized Optimal Subpattern Assignment.
TGOSPA. Okay, what does that measure?
It's more comprehensive than just looking at point errors. It evaluates the overall quality of the entire trajectory. It penalizes errors in position, yes, but also penalizes misdetections, false detections, and crucially, identity switches, where the tracker mixes up which track belongs to which particle.
So it captures the whole picture.
Right.
And lower is better.
Yes. Lower TGOSPA scores mean better overall tracking accuracy. They also reported some other metrics like point precision recall and link precision recall, PL and RL, which give you a more detailed look at specific types of errors, like how good it is at connecting points correctly versus how many true connections it finds.
Okay, let's get to the results then. Based on these metrics, what did the paper find? How did ABHA do against MHT, especially on that key TGOSPA metric?
The key finding is that ABHA consistently achieved lower, meaning better, TGOSPA scores compared to MHT. On most of the really challenging tasks, the ones designed to be cluttered and noisy, they label them tasks 1 through 4, and also under medium particle densities.
So in the messy conditions it was designed for, ABHA generally produced more accurate overall trajectories.
That's what their data suggests, yes. Interestingly, MHT actually performed slightly better on TGOSPA, but only in what they call the idealized baseline task, which had basically no noise or clutter.
The easy case.
The easy case, where MHT's more aggressive strategy perhaps worked fine.
So why does ABHA seem to shine particularly in the clutter, according to the paper's analysis?
They attribute it to what they call ABHA's conservative strategy. Remember, the transformer is trained to find high confidence associations based on learned patterns. So ABHA tends to make selective, high confidence associations.
It only links things when it's pretty sure.
Exactly. And the consequence of this conservative approach is fewer false positives. It's less likely than MHT to mistakenly link a random noise point to a real track. Since TGOSPA heavily penalizes those false positives, this carefulness really helps ABHA score in noisy, cluttered situations.
That makes a lot of sense. Being cautious avoids certain types of errors, even if it means you might miss a few things.
Precisely. And you see that trade-off reflected in the other metrics they report, specifically the link metrics. ABHA generally showed higher link precision, ABT, but lower link recall, RL, compared to MHT.
Okay, precision versus recall. Remind us what that means here.
I-link precision, PL, means that when ABHA decides to link 2 points together to extend a track, that link is very likely to be correct. It makes fewer mistakes in the links it forms.
Okay, high accuracy in the links it does make.
Right. But lower link recall, RL, means that ABHA misses more of the true links that actually exist in the data compared to MHT. MHT is more aggressive. It tries to link more points, so it catches more of the true links, higher recall. But it also makes more mistakes by linking things incorrectly, lower precision.
So it's a trade-off. MHT is like, link everything that looks plausible, gets more right, but also more wrong. ABHA is like, only link if I'm really sure, gets fewer wrong, but also misses some opportunities.
That's a really good summary of the dynamic they describe. So
Yeah.
the authors are quite nuanced in their conclusion. They don't claim ABHA is universally better. They position it as a conservative yet accurate tracker, particularly suited for cluttered regimes. Its advantage comes from that learned pruning strategy, which pays off most when things get really messy.
Okay, that paints a clear picture of its strengths and weaknesses based on their evaluation. What limitations did the authors themselves acknowledge in the paper? And what's next for this line of research?
They're commendably upfront about the limitations. First, the testing was done on just one main type of particle motion, the sort of stop-and-go mixed Brownian directed motion from the virus's data set. They definitely need to test it on a broader set of motion types to see how well it generalizes.
Because real biology has all sorts of movements.
Absolutely. Second, as we mentioned, the tests were on those small 30 by 30 patches with only about 20 particles. That's useful for proof of concept, but it's not a full-scale benchmark. They explicitly state a goal to scale up to a larger field of view for more standard comparisons.
Makes sense. Prove it small, then go big.
Exactly. They also note that MHT consistently gets better recall scores, RP and RL, and they need to dig into why that is to potentially improve ABHA. And they observe the performance gap narrows in low-density scenes, which also needs more investigation.
And the overall goal, where do they want to take ABHA?
Well, ideally, they'd like to improve it to outperform MHT across the board, on all metrics. But perhaps more realistically in the near term, they want to achieve a more generalizable training so it can handle diverse, biologically relevant movements, making it a more versatile tool for scientists.
This has been a really illuminating deep dive into ABHA.
It really is a fascinating example of smart engineering, isn't it?
Yeah.
Taking this really tough computational problem and finding a way to combine different philosophies, the pattern-finding power of deep learning attention for the association chaos,
Right.
and then falling back on the proven reliability of Bayesian filtering, like the Kalman filter, for the precise state estimation once the problem is simplified.
It definitely highlights that modular approach. Break down the big problem, use the right tool for each part.
Yeah. Use the learning for the messy combinatorial part. Use the established statistics for the tracking part. It seems like a really promising direction for handling these incredibly complex but important tracking tasks in biology, trying to see what's actually happening inside living cells.
Definitely. So, thinking beyond this specific paper, let's leave you, our listener, with a final thought to chew on. We've seen how effectively ABHA combine learned pattern recognition, that attention mechanism, with established statistical filtering, the Kalman filter, to solve this tricky particle tracking problem. Where else could this kind of modular hybrid approach work? Where else do we face complex data association problems, maybe in science or engineering, that could benefit from using AI to prune possibilities before applying more traditional analysis? Perhaps correlating noisy signals from many sensors, or maybe tracking interacting objects in complex videos.
A great question. That blend of learning and modeling could be powerful in many domains.
Something to think about. Thank you for joining us for this deep dive into the Attention-Bayesian hybrid approach.
It was a pleasure.